So you see the title of my talk, Proofs as Objects, the second phase of proof theory. The mathematical substance of my talk is rooted in two areas of interacting proof-theoretic work. On the one hand, the pursuit of extensions of Hilbert's finitist consistency program, and on the other hand, the detailed formalization of mathematical proofs. Issue one, well, that is not. The significance of results obtained in the pursuit of extending Hilbert's program depends crucially on two factors. Which constructive principles are being used in the consistency proofs, and which parts of mathematics are actually covered by the formal theories shown to be consistent. The first issue, concerning constructive principles, has been much discussed in the foundational literature. The second issue, concerning the principles actually used in the formalization of mathematical proofs, has also received much attention, but with an almost exclusive focus on axioms and the bare inferences of logical calculi. The subtle methodological question I just hinted at is, or I will argue should be, at the heart of proof theory and constitutes its second phase. The second phase is directed towards the discovery of the actual structure and the efficient construction of mathematical proofs. Such investigations have, to my knowledge, not been pursued in any systematic way. Recently, this methodological question has become a central issue, namely through work on computer-based formal verification and automated proof search. The issue, I think, is reflected in the question, what methods can actually be used in such work? Using a distinction that goes back to the 1950s and 1960s, it has been emphasized that two different methods can be used, machine-oriented and human-oriented ones. The machine-oriented techniques have been mostly refinements of resolution. The human-oriented ones range, and I'm referring now back to the 50s and 60s, from pure heuristics, as in the work of Newell and Simon, to incorporating aspects of natural deduction, as in Woody Bledsoe's work, and in the work of a cognitive psychologist, Lance Rips. Gowers, in collaboration with Gentzen, has recently pressed for human-centered automatic theorem proving, and he wants to pursue this as a way to teach to mathematicians proof finding and proof writing. Their work was published in the Journal of Automated Reasoning in 2017. With a student of mine, I analyzed that paper very carefully and compared the Gentzen and Gowers prover with the automated theorem prover APROS I have been developing over quite a number of years. The resulting paper, both an analysis of the paper by Gentzen and Gowers, and the comparison was published also in the Journal of Automated Reasoning a couple of months ago. Just one interesting observation, the APROS system can do what the GNG prover does in a very small fragment, It is just minimal logic. That's it. And whatever proof search methods are being used, they are easily obtainable and incorporated in a process. So, some history. I mean, you would expect this from me, I suppose. Though reawakened by recent work, there are early articulations of proof theory in the 19th century, e.g., in projective geometry and theorems concerning duality. Hilbert's 24th problem, that was discovered only more recently by Thiele, but formulated obviously in the context of the Paris problems, requested a theory of a method of proof in mathematics in general, and raised issues of proof simplicity and identity. Formalisms thesis, that was defended in 1908, started out investigating and classifying partition proofs of the Pythagorean theorem. In none of these proof-theoretic work was a logical calculus, a logical language involved whatsoever. It was only at the beginning of 1913 that Hilbert and his circle became familiar with Principia Mathematica and the logicism of Whitehead and Russell. Of course, they knew a little bit about Frege, but that did not impact Hilbert in a really strong way. Impacted by those logical developments, Hilbert gave a programmatic logicist talk to the Swiss Mathematical Society in Zurich on September 11, 1917. The talk was called Axiomatisches Denken, Axiomatic Thought. For us, it is important that he called there also quite emphatically for a theory of the specifically mathematical proof. Let me show you a picture, a photo, that is, of the participants of this meeting of the Swiss Mathematical Society. And you see Hilbert in the middle of this picture, and to his right, or rather to his left, Hermann Weil. Bermas is in the background. Oh, I should mention that Hilbert, at this very meeting, at this very stay in Zurich, hired Paul Bermas as his assistant for foundational work, foundations of mathematics. In lectures of the following winter term, 1917-1918, Hilbert took important steps. The lectures he gave were written up by Bermas, about a text of about 220 typed pages. About 50 of those are devoted to an example of the axiomatic method in geometry, and the remainder is titled Mathematical Logic. And it is a remarkable piece. It presents mathematical formal frameworks in a mathematically rigorous way. So it is in that sense mathematical logic. And it also gives a detailed formalization of parts of number theory and parts of analysis. As a side note, I just wanted to mention, these lectures are the real beginning of mathematical logic. It is not the book by Hilbert and Ackermann that is so frequently seen as the starting point of mathematical logic. Hilbert and Ackermann's book consists about 90%, literally, of the notes Bernas took in 1917, 1918. In any event, the most significant part or step for us is his detailed formalization of parts of analysis, in essentially second-order arithmetic. But the formal frame was viewed as a part of Principia Mathematica, using the axiomal reducibility. And in particular, the logical calculus that is presented in Principia was used in their deliberations. I should emphasize that this investigation of mathematical truths by means of a rigorously formulated logical calculus was a discovery and showed that, and I quote Hilbert and Berners, the concept formations and the inference patterns used in the theories of analysis and set theory are reducible to a limited number of processes and rules. In that way, we succeed in totally formalizing these theories within the frame of a precisely delimited symbolism. And to just make a remark about the claim that it was a discovery for Hilbert. Hilbert gave from roughly 1905 through these lectures in 1917, lectures on the foundations of mathematics almost every single year. And you see what he considered to be logic, a little bit of algebraic logic. There was no reference to anything else. The first time that mathematical logic in our sense is being presented is in these lectures from 1917, 1918. For pragmatic and methodological reasons, Hilbert and Berners introduced in the winter term 1921-22 a new logical calculus. It is an axiomatic formulation of natural deduction and was used throughout the 1920s and 1930s. And you see the axioms, and I wrote down on the left-hand side the names of the corresponding natural deduction rules. So I say for pragmatic and methodological reasons. Pragmatic reasons, they thought that this calculus allowed a much more direct and easier formalization of mathematical argumentation. And methodological, Hilbert wanted to do for logic what he had done for geometry in Grundlagengeometrie, namely articulate groups of axioms for each geometric concept, and here for each logical connective. And I should mention that in their consistency proofs that were given around this time for very weak quantified refinements of arithmetic, they introduced a tree representation of deductions in this calculus. Gentzen built on their work in his dissertation 1933 when formulating the natural deduction calculus. There he asserted that the calculus is as close to real reasoning, wirkliches Denken, as possible. Thus, so he wrote, the calculus is particularly suited for the formalization of mathematical truths. In his 1936 paper, in which he proved the consistency of LM number theory, he considered formal derivations in the natural deduction calculus as images of mathematical truths. Indeed, he wrote, the objects of proof theory shall be the proofs carried out in mathematics proper. So let's this remark sink in for a little bit. Gentzen's interest was shared by one of his Göttingen friends, who completed also in 1933 a thesis written at first under Berners and then after Berners' dismissal from his position by the Nazis, under Hermann Weyl. That friend of Gentzen's wrote many years later, 1979, about this early logical work, there remains the real question of the actual structure of mathematical proofs and their strategy. It is a topic long given up by mathematical logicians, but one which, still properly handled, might give us some real insight. And perhaps you know to whom I'm referring as Gentzen's Göttingen friend. Does anyone know? Yes, no? Well, it's Saunders MacLean. So I have been since the mid-1980s interested in related matters, namely the fine structure of mathematical proofs reflected in appropriate logical frames, strategic ways of constructing proofs interactively, heuristics for the automated discovery of proofs. That this interest put me into this tradition of genuine work by proof theorists, I didn't realize until the late 90s. But in any event, so this is the historical part I wanted to present to you, because I think it is important to realize that in a certain sense, proof theory was what mathematicians frequently think it should be, namely a genuine theory of mathematical proofs. There is this second part to it, and that's what I wanted to emphasize. So let me tell you, or give you an overview of the remaining parts of my talk. In part B, I discuss logical calculi and articulate bidirectional frames. In part C, much shorter, I want to give an example of natural formalization. It's the formalization of the Cantor-Bernstein theorem, using as one central step Dedekind's lemma, which I'm going to formulate, of course. And even more briefly, I'll point to an example of automated search, namely an automated search for Gödel's incompleteness theorems. And I should mention right away that I take for granted in this search representability and derivability conditions, and also the articulation of particular self-referential sentences, like the Gödel sentence or the sentence that is used in Löb's theorem. Okay, bidirectional frames. We saw Hilbert and Berners' axiomatic calculus that articulates natural reduction rules as axioms. Or rather, Gentzen turned the axiomatic formulation into his rule-based system. And I mean, I'll just give you examples of rules and axioms as I did before. Gentzen viewed as distinctive for his natural reduction calculus not the interplay of introduction and elimination rules, but rather the making and discharging of assumptions. That reflected for him an important structural element of proofs in mathematical practice. That emphasis reveals, however, also an unnatural feature of natural reduction. So, for example, to prove A or B, one assumes A and tries to establish B. That proof context is not part of the syntactic configuration one uses to start the sequence of proof steps. One just writes down the assumption A and then proceeds. So for me, the question is, can one reflect the proof context of goals and assumptions in a direct way through a proof configuration, a syntactic configuration? And in such a syntactic configuration, can one make goal-directed forward and backward moves? And what does it mean? And how can one articulate that a forward step is goal-directed? In any event, the first step can be taken via Gentzen's sequent formulation of natural deduction in 1936. And calling this formulation sequent formulation is not my invention. It was used by Gentzen. Sequenzenformulierung des natürlichen Schließens. That sequent formulation indicates locally at each proof node on which assumptions the proof for the formula depends. And it also presents the proof context. So here you see two examples. The elements of gamma are just the assumptions on which phi depends. And here you have a proof of disjunction. And in order to give the argument by cases, one has the additional assumption of the left disjunct here to obtain what one wants to obtain, and the right disjunct on this side. But you should observe that all the rules, the logical rules, so to speak, operate on the right-hand side and retain another quite unnatural feature of natural deduction, namely that it allows detours. That is, that an elimination step follows directly an introduction step. The second step that leads essentially to Gentzen's sequent calculus with elimination rules applied on the left-hand side and introduction rules on the right-hand side. However, the applications of the elimination rules are in general not goal-directed. So I'm going to give you a redescription of the logical problem to be addressed first, and then indicate a third step. The redescription is as follows. Close the gap between assumptions and a goal by two ways of proceeding. By exploiting assumptions via sequences of E-rule applications that are goal-directed, and simplifying goals via inverted introduction rules. So if you think of natural deduction derivations, you would have a sequence of elimination steps from the top in a forward direction, and a sequence of introduction steps from the bottom up. That's what I've been calling intercalating. That is, the logical problem is addressed by a species of goal-directed forward and backward chaining. And now I'm going to give you one example of a rule of a calculus that I call natural intercalation calculus, NIC calculus, that involves extraction sequences that specify goal-directedness and having structured sequence at every proof node. And let me give you one example. I mean, there are actually 3 examples on my slide, but I only want to focus on one example, namely the AND elimination. So you see, this is not exactly the sequent calculus. So we start from the bottom up, and if you want to apply an elimination rule. But the elimination rule is supposed to be applied in a goal-directed way. And the goal-directedness towards the goal that is to be achieved, namely a proof of chi, is given by an extraction sequence. What is an extraction sequence? Well, this elimination, the elimination rules can be sensibly applied in a goal-directed way only if, as a matter of fact, the goal formula is a positive subformula, strictly positive subformula of an assumption. The extraction sequence gives then the individual elements of the immediate subformula relationship between the element of gamma and chi. And that's what is indicated here. You have achieved via elimination steps gamma, semicolon, delta, phi, and psi. That is an initial segment of the extraction sequence, and you apply, depending on what sigma actually tells you, the extraction sequence, either phi or the other conjunct psi. So that is the way in which formulas are intercalated between assumptions and goals. The Dick calculi for classical and intuitionist first-order logic are complete. And the proofs that one obtains are essentially normal natural reduction proofs. And it is the combination of the big steps that one is taking in constructing a proof that is implemented into the proof search algorithm APROS. There is, first of all, extraction. You want to see whether, in a quite direct way, by just exploiting what is given to you, the goal can be achieved. If that can't be done, then one analyzes the goal. If it is logically complex, one uses the appropriate introduction rule in a backward way. And if that doesn't lead to a goal either, or to a proof either, one uses, in classical logic, refutation, or in intuitionistic logic, just explicit quadruped. That is the crude structure of this strategic search. There are many, many details, in particular as far as extraction is concerned, that one has to consider. And obviously, perhaps not as obviously, but in any event, that is the basic search strategy. Try to extract. If that doesn't work, invert. If that doesn't work, if you're an intuitionist, try to use explicit quadruped. If you're a classical logician, use also refutation. Okay. So, to summarize in a certain sense, we have calculi that support a bidirectional and goal-directed proof construction in both intuitionist and classical first-order logic. But in the same way as ordinary natural reduction trees, such NIC proofs are not easily displayed on a computer screen. So we chose a graphical display that is inspired by the representation of natural reduction proofs by Fitch diagrams. But there is one dramatic and important difference. At first, it may not seem to be such a big deal, but it is. Namely, one cannot make an arbitrary assumption at any point in constructing a Fitch diagram. So let me put it this way. I misspoke. In constructing Fitch diagrams, you can at any point make an arbitrary assumption. That's what I call free assumption. And that cannot be done in the diagrams I'm going to show you in a second. And that is possible only because of the bidirectionality of the Nick rules. So here, an example from a proof in the what we call logic lab or proof lab. You want to prove P or not P. This is the interface of the system. There are rules on the left-hand side, or logical rules. And if you choose this P or not P as the goal, and you think of applying negation, elimination, refutation, in the rule preview, it shows you the effect of the rule application, and then if the user applies that particular rule, the first step is being taken, and it is this. So you have now an additional assumption, not P or not P, and you have to prove a contradiction. But as you know, the choice of contradictory pairs is rather restricted in natural reduction and also in this calculus. The negated part of such a contradictory pair has to be a positive subform of an assumption. And so we know in this particular case, one has to establish P or not P. And how does one do that? Well, now you do inverted introduction of the discharging, and you can either choose P or not P, doesn't matter. And then for not P, you do exactly what we did previously, namely, you have the not introduction rule that goes from the assumption P, oh sorry, I should not have told you yet, from the assumption P to obtain a contradiction, and this is then directly done, leading to this particular proof. I gave this only not because that is a difficult logical theorem, but to show you how the strategic moves are going to be joined to obtain in a motivated by a proof. So I wanted to make a few remarks about the evolution of this work. I started this in 1986 when I had moved from Columbia University to Carnegie Mellon. And the logical work went hand in hand with the implementation of search procedures, first for classical and intuitionist sentential logic. And I should also tell you, I mean, I didn't consider this to be the central part of my research, so I did it more or less on the side with a couple of colleagues. The step to full first-order logic took a number of years, and the reason for it is very simple. I didn't know how to extend the strategies I was showing you, how to extend them to predicate logic. That is, what was difficult was having extraction available for formulae that involve quantification. In any event, I had an idea that worked. And so the first presentation for classical logic was in 1992, and more fully in a longish article in Studia Logica in 1998 with my student John Burns. And then for intuitionist logic in 2005. So you may have wondered if I didn't consider this to be part of my real research, why did I get into it? I wanted to have an introduction to logic that encourages individual learning. And I had seen how this can be done when I was a graduate student at Stanford and worked in the Institute for Mathematical Studies and the Social Sciences that was directed by Patrick Soukis. So I wanted to develop a web-based interactive logic course. But that began only in 2007. The proof theoretic work I described, I wanted to have done that before developing the course. Because my main idea was you have an interface in which students give proofs. And if a student is stuck, then he or she can appeal to a proof tutor. The proof tutor gives the partial proof the student has constructed to the automatic theorem prover, and it completes the proof, possibly with backtracking. And then, based on this completed proof, the tutor can actually give advice to the student. In any event, we began developing this web-based course in 2007. It took much more time than I ever thought it would. And in 2011, I had a version that I thought was sufficiently sophisticated and bug-free that it was offered also not only by me at Carnegie Mellon, but at other institutions as well. And by now, this course has been taken by 14,000 students for credit at their home institutions. It is not a MOOC, but it is literally taken at other institutions on servers at CMU, but the course is a proper course and at the other institution. Okay, so much about the evolution of this work. Let me move on to part C, natural formalization of mathematical proofs. The natural formalization of mathematical proofs is achieved by extending the rule-based strategic approach to include defined notions and operations. So one has introduction and elimination rules for defined concepts. In addition, one applies lemmas as rules, both forward and backward. Lemmas that are of a very simple syntactic form, namely conditionals, where the antecedent may be a conjunction of formulae. And so if one has established in the proof all the conjuncts of the antecedent, then one can use the lemma as a rule to infer the consequent. And on the other hand, that is the forward move, right? On the other hand, if one tries to establish a particular goal, and one is looking, how could I possibly do this? And one recognizes that there is a lemma that has this goal as its consequent. Then one can try to prove the conjunctive parts or the antecedent of the lemma. That is obviously a background move. But that requires obviously a careful conceptual organization. Patrick Walsh and I formalized in this natural way the counterdanstat theorem in Zermelo Frankel set theory. Our paper was published in the Review of Symbolic Logic 2 years ago. But I also wanted to show you in a very colorful way that this is not a novel idea. It reflects mathematical practice in the most striking and beautiful way. Here is a colorful depiction of the Pythagorean theorem. That is, as you know, proposition 47 of book 1 of Euclid's Elements. What is being done? There is one central lemma that is being used, namely what is called by in American high school geometry books the SAS lemma or theorem. So as soon as you know that you have two triangles with two equal sides and the enclosed angles are the same, then the triangles are congruent or equal in Euclid's terminology. In this case, you're looking at the triangle ABC and the triangle DCE. Now you notice also that this line, this side of the first triangle I pointed out, is equal to that side of the triangle of the other triangle. And similarly, this line is equal to that one. So we have two, equal sides of the two triangles, and the enclosed respective angles are also equal. Look at the triangle ABC. The enclosed angle is the right angle or the square, together with this little black angle. Right angles are identical, equal, according to one of the Euclidean axioms. So if you take the yellow angle, this one, and add to it the black angle, you get the same angle as when you're adding that black one to the blue right angle. So the conditions for the congruence or equality of those two triangles applies. And then one just has to see by a few elementary steps that are lemmas in the development of Euclid's book 1, that this triangle ABC equals half of the red square, and the triangle DCE equals half of the yellow rectangle. And then by an easy computation, you obtain 1/2 of the proof, and then you do the same thing for the black square and the blue rectangle. But the point is very simple. You use lemmas, and sometimes very crucial lemmas, to obtain an interesting and important result. So the counterdanstat theorem, as you know very well, it's formulated as follows. You have an injection from A to B and an injection G from B to A. The claim is there is bijection H from A to B, that is, A and B are of the same size. The counterdanstat theorem is easily proved from, and as a matter of fact easily proves, also Dedekind's fundamental lemma that is formulated in Dedekind's essay Was sind, was sollen die Zahlen? You have a bijection from a set A to a subset of itself. And in addition, you have a set D that lies between the set A and the subset with which you have this bijection, so that you have this inclusion E is a subset of D is a subset of A. And the claim is, then there is a bijection H star from A to D. So, say it once more, you have a bijection from A to E, and you have this inclusion relation, and then there is a bijection from A to D, this intermediate set. That's a sort of sandwich there. And here's a depiction of how, given that you have this fundamental lemma of Dedekind's and some understanding of the notions concerning sets and functions, how you get the proof. You have the set A, you have the function, the injection, f from A to B, you have B, and the injection from B to A, and then immediately you realize that just using the understanding of being the image of a set under a given function, that inside of A, you have this subset relationship. But in addition, you also know almost immediately, given that F and G are injections, that A stands in a bijective relationship with this most interior set that is obtained as the image of the composition of F and G of A. Now, G of B is, of course, a superset of it, but still in A. And so everything has been verified that you can apply the fundamental lemma to obtain a bijection between A and G of B. And that is, of course, of the same size as B. And that's it. So the considerations are very simple. You can just use an informal understanding of the notions of set and function, the counterbalance there, using the fundamental lemma. And that is the crucially interesting part, which I'm not going to discuss with you. But it's a wonderful construction. So the final proof in the F that Patrick and I built rests on about 100 lemmas. But the lemmas referred to in our formal proof articulate the direct facts for the concepts of set and function I just used in the informal. And here it is. It's a proof of 8 lines, as a matter of fact, just 6 lines, because the first 2 parts are just the articulation of the premises of the counterbalance theorem. This first one says, well, there's a bijection between A and the smallest subset of A. G of B is a subset of A. G of B is larger than, is of greater size than the image of A under G circle F. And then the fundamental lemma gives you line numbers 8, line 7 is trivial, and thus you have the fact that A and B are the same size. So clearly, there are lots and lots of small things that have to be verified in order to get a full, completely formal proof of this theorem. I mean, for one, all of these lemmas have to be established. But that's what I think can be done to give formalizations that lead to intelligible good proofs. And let me make one remark. There are presumably many, many different proofs of the counterdeduction theorem. In our paper, we actually investigate quite a few different, presumably different proofs. But in the end, the core of the mathematical argument leads to exactly two different proofs. One is Dedekind's 1887 proof, and the other is a proof Zermelo gave in his first paper in which he articulated the principles for Zermelo set theory. And those two proofs make use of Dedekind's chain theory, but Zermelo didn't know anything about Dedekind's 1887 proof. That was revealed that it existed only in 1932. In any event, those two proofs differ in the way in which they make explicit inductive definitions. And the difference has a very beautiful mathematical description. One can associate with Dedekind's inductive definition, a monitor operator. And then Dedekind's explicit definition is the smallest, Zermelo's is the largest fixed point of that very operator. And as far as I can make out, I mean, there's this beautiful book by Hinkes on proofs of the Schröder, of the Cantor-Bernstein theorem, in which, on roughly 400 pages, lots and lots of presumably different proofs are described, and the intellectual mathematical background is discussed in informative ways. But the proofs I examined have, as I said, at its mathematical core, either Dedekind's proof or Zermelo's proof. And the only difference is the way in which they make explicit inductive definitions. So I wanted to discuss automated proof search, but I also realized that I'm transgressing beyond my time. So I'm going to leave this out. It was in any event a very abbreviated discussion. So let me just jump over it, because I think to explain this more fully takes, after all, a little bit more time. The only thing I show you a picture. So that is the formal proof of the first half of the first incompleteness theorem, the unprovability of the Gödel sentence tree. But another time. Let me make some concluding remarks. And let me return to Hilbert's 1917 call for a theory of the specifically mathematical proof. I think we have taken steps towards such a theory by introducing the big calculi that make it possible to reflect important structures of mathematical truths. And the bidirectionality and the resulting features one can use in constructing proofs, that is the important part. I described some meta-mathematical results for the Nick calculi and discussed their use for natural formalization and hinted at automated search. It seems to me that such work allows us to illuminate the second phase of proof theory and bring it to life are the analysis of mathematical proofs, their formal presentation in suitable formalisms, and the expansion of the heuristics to find intelligible proofs fully automatically. In this way, I hope we will uncover capacities of the mathematical mind and, more broadly, of the human mind. After all, mathematics is common sense, made rigorous. Thank you so very much. And let me, okay.
Thank you so much for the great talk. Thank you. I'm going to stop the recording now, as we always do before the question session.